All right, so according to my notes, we did these four problems on page 1, and then we did example E on page 2. Are you guys in agreement with that? Okay. So let's take a look at example F. We have the natural log of x minus 2 plus the natural log of 2x minus 3 is equal to 2 times the natural log of x. Now, on the left-hand side, we can condense that using the product rule of logarithms. Remember, the natural log of A plus the natural log of B is equal to the natural log of A times B. Okay? Let's call it the product rule. So using the product rule, the left-hand side, right, this is like our A, and this is like our B. And so the left-hand side condenses to the natural log of x minus 2 times 2x minus 3. So remember, what's inside the brackets here is called the argument. Because that's the argument going into the natural log. On the right-hand side, okay, this 2 in front of the natural log can be brought inside the natural log and made an exponent of the variable x. So we have the natural log of x squared. So I use here both the product, I use the product rule on the left and the power rule on the right. Now, x squared is the argument going into the natural log function on the right-hand side, right? I'll put it in parentheses to emphasize that. So we have the natural log of this argument is equal to the natural log of that argument, okay? And since the left-hand side equals right-hand side, the two arguments must be equal, okay? Taking the natural log of this argument is equal to the natural log of this argument. Since the left-hand side equals the right-hand side, this argument must equal that argument. Okay. Now you can also, because the left-hand side equals right-hand side, make the left-hand side an exponent of the number e, and the right-hand side an exponent of the number e, and then the e and the ln cancel, and you're left with this argument is equal to that. Okay. Two approaches. Okay. So the arguments x minus 2 times 2x minus 3 has to equal the argument x squared. Okay. This is shaping up to be the quadratic equation that we're going to solve. So, we got to FOIL the left-hand side. And so when we FOIL, we have x times 2x, which is 2x squared. When we multiply outer terms, we have minus 3 times x. When we multiply inner terms, we have minus 2 times 2x, which is minus 4x. And then minus 2 times minus 3 is plus 6. And that's equal to x squared. FOIL. Now the left-hand side, combine like terms, and 2x squared minus 7x plus 6 is equal to x squared. And now you can subtract x squared from both sides to get 0 on the right hand side. And 2x squared minus x squared is x squared. And x squared minus 7x plus 6 is equal to 0. And that factors with whole numbers. That factors into x minus 6 times x minus 1. So by the zero product property, either the first factor is equal to 0 or the second factor is equal to 0. So you get, when you solve those two equations, you get x is equal to 6 or x is equal to 1. So those are the two solutions, okay, to our quadratic equation here. But only one of them is a solution to our original equation. One of them is called an extraneous solution. It's a bogus solution to our original problem. Do you know which one it is? You can't take the log of 0 or negative number, right? So if you put 1 in for x here in this argument, you have 1 minus 2, which is negative 1. And the natural log of negative 1 does not exist, right? And same thing over here. Put 1 in for x. 2 times 1 is 2. 2 minus 3 is negative 1. And the you can't take the natural log of a negative 1, of a negative number. It's undefined. So the only value of x that works in our original equation is 6. 6 minus 2 is 4. 2 times 6 minus 3 is 9. Right? And you can take the natural log of plus 6. So you guys scratch out x equals 1 because it's an extraneous solution. X equals 1 is a solution to this quadratic equation, but it's not a solution to our original problem. Right? We created that extraneous solution when we condensed the left-hand side with the product. All right. Any questions on that? All right, so if you flip over to page 3, we got 4 more examples. G, H, I, and J. Those, I have the solutions to those 4 problems on video. I will post a link on Oaks and send you an email with the link. Remember, we missed 2 classes because of Hurricane Ian, and this is part of that makeup. Okay? So I will send you the link, right? And it's just me writing the solution on the board, just like I did here. Okay. All right, so now if you flip over to page 4, we're going to find a couple of inverse functions. So in 2a, you're given the function f of x is equal to e to the 3x minus 1 power plus 5. We got to find the inverse function, f inverse of x. Okay. So you should note that f of x is the transformation of the natural exponential function. graph looks like that, right? This graph passes horizontal line test. So this function is just a transformation, right, of the natural exponential function. So this function has an inverse. Okay? 4 steps in finding the inverse of any function. Replace f of x with y. Step 2, switch x and y. So we replace f of x with y, and now we switch x and y, right? Replace y on the left with x, and we replace x on the right with y. Okay. And step number 3, solve for y. So, right, got to isolate y on one side of the equal sign. So, first thing you would do, right, subtract 5 from both sides, right? Move the 5 to the left-hand side by subtraction. And we have x minus 5 is equal to e raised to the 3y minus 1 power. Now, what's the inverse function of the natural exponential function? It's the natural log function, right? So we can take the natural log of both sides, and we have the natural log of x minus 5 is equal to the natural log of e raised to the 3y minus 1 power. So on the left, we have the natural log of x minus 5. But on the right-hand side, right, the natural log function and the natural exponential function are inverse functions of each other. Right? So they cancel, and we're left with 3y minus 1, the exponent of 3y minus 1. And now I can move the minus 1 to the left-hand side by addition, add 1 to both sides. Now when I do this, I could put it after the natural log, but I don't want to confuse the plus 1 with the argument going into the natural log. So I'll put the 1 in front of the natural log. And then lastly, I'm going to divide both sides by 3. And we have 1 plus the natural log of x minus 5 divided by 3 is equal to y. And now I flip the two sides and replace y with inverse function notation. And since our 1, function is f, our inverse function is f inverse of x, which is equal to 1 plus the natural log of x minus 5 over 3. Use interval notation to state the domain and range of the inverse function. Okay. Well, the domain this plus 1 and this plus 3, right, don't affect the domain. What affects the domain is the x inside the argument, right? In the argument to the natural log function. Remember, you can't take the natural log of 0, and you can't take the natural log of a negative number. So to find the domain, we set the argument x minus 5 strictly greater than 0. argument going into the natural log function has to be positive. Can't be 0 or negative. And then when you solve for x, you add 5 to both sides, you get x is greater than 5. So the domain is all real numbers greater than 5. So that's what you put in down here. Now, probably the easiest way to recognize the range of the inverse function is you know that the graph of the natural log function looks like this. We talked about the domain and range of the natural, right? Y equals the natural log of x. There's no minimum y coordinate, there's no maximum y coordinate. When you replace x with x minus 5, all that does is shift this graph to the left 5 units, or to the right 5 units. There's still no minimum y coordinate, there's still no maximum y coordinate. And adding 1 to the function, okay, let's do it this way. So here the graph crosses at x equals 1. When I replace x with x minus 5, this whole graph gets shifted to the right 5 units. So that it crosses the x-axis now at x equals 6. And then if you add 1, right, and divide by 3, right, you're just shifting the graph up, and you're stretching it by a factor 1/3. So the 1 and the 3 really don't affect the y coordinates. There's still no minimum y coordinate, there's still no maximum y coordinate. And so the range is minus infinity to plus infinity. Those of you guys take Math 120, you really need to be familiar with the natural log function, graph of the natural log function, natural exponential function. So any questions on this, ladies and gentlemen? Yes, ma'am.
Would there be any transformation that would change the range?
Say what?
Would there be any transformation that would change the range?
Not of this nature. Yeah, okay. All right, in B, we have f of x is equal to the natural log of x plus 3 minus 1. So x plus 3, right, is the argument going into the natural log function. And so you know from the graph of the natural log function, right, it passes the horizontal line test, so it has an inverse, and the inverse is the natural exponential function. Okay? And replacing x with x plus 3 just shifts this graph to the left 3 units. And then subtracting 1 shifts it downward. Well, we got at the bottom it says use interval notation to say the domain and range of the inverse function. Well, you know the range of the inverse function is equal to the domain of f of x, right? So we can find the range right away by writing out the domain of f of x. Set the argument going into the natural log function greater than 0. And you get x is greater than minus 3. So in interval notation, the domain of f of x is all real numbers greater than minus 3, but that's also the range of the inverse function. We haven't even found it yet. Okay. The domain of f of x is the range of f inverse of x. Right? All right. So to find the inverse function, first replace f of x with y. Now we switch x and y. And now we solve for y, right? So I can move the minus 1 to the left-hand side by addition. And so I have x plus 1 is equal to the natural log of y plus 3. You know the natural exponential function is the inverse of the natural log function. Left-hand side equals right-hand side. So I can make the left-hand side and the right-hand side exponents on the number e. So I have e raised to the x plus 1 is equal to e raised to the natural log of y plus 3. Left-hand side equals right-hand side. So I can have e to the left-hand side is equal to e to the right-hand side. Well, natural exponential function, natural log function are inverse functions of each other. They cancel. And we're just left with y plus 3 on the right-hand side. And now I subtract 3 from both sides. I have minus 3 plus e to the x plus 1 is equal to y. And now I switch the two sides and replace y with inverse function notation. And I have f inverse of x is equal to minus 3 plus e raised to the x plus 1 power. Now, it is probably to see the range of the inverse function. It's probably easier. Okay, so let me back up. So the domain, excuse me, the range of the inverse function, right, is equal to the domain of f of x, which is minus 3 to infinity. Right? The y coordinates are all greater than minus 3. To see the domain of the inverse function, it might be easier to look at the range of f of x. The graph, this is the graph of y equals the natural log of x. So when you replace x with x plus 3, it just shifts this graph to the left 3 units. Instead of the graph crossing at x equals 1, it now crosses at x equals minus 2. Right? It shifted to the left. So this is y equals the natural log of x plus 3. And then when we subtract 1, it just shifts the graph down 1 unit. So there's no minimum y coordinate, there's no maximum y coordinate. Right? After you shift this graph to the left 3 units and shift it down 1 unit, there's still no minimum y coordinate, there's still no maximum. So the range of f of x is all real numbers. No minimum y coordinate, there's no maximum y coordinate. So that means the domain of f inverse of x is equal to the range of f of x, which is all real numbers. Okay? Are you with me? That makes sense? All right. So once you watch the video and get those final 4 solutions, you will be able to successfully complete the web assignment homework. Do 1 week from today. All right, 5.4 is a short section. So you don't have to. One for you, one for you, one for you, and then can you and her three for her, and the 2 gentlemen behind her. All right. So 5.4 utilizes everything that we learned about the natural exponential function and the natural logarithmic function. So we're going to do a little mathematical modeling. So in the rectangle at the top of page 1, we're told that the exponential growth model is used to model the quantity of a substance or population that grows with time. And so this is the basic model, basic exponential growth model. Okay. The amount of a substance or population at time t, right? T is time. And normally t is greater than or equal to 0. We do not allow for negative time. The amount of a substance at time t is equal to a sub 0, which is a constant, times e raised to the kt power. So a sub 0 and k are both constants. T is the variable that changes, okay? T for time. So this is what is called an exponential growth model, using the number e. A of t is equal to the amount of substance or the size of the population at time t. A sub 0, which is equal to, or excuse me, A of 0, which is equal to A sub 0, is called the initial amount or initial population. So if you plug 0 in for t up here, right, you have A of 0. You have A of 0 is equal to A sub 0 times e to the k times 0 power. Well, k times 0 and the exponent number e is 0. So this is equal to A sub 0 times e to the 0. And e to the 0 is equal to 1. And A sub 0 times 1 is equal to A sub 0. that's how we got this, that A of 0, right? The amount at time t equals 0 is equal to A sub 0 is called the initial amount or initial population. The constant k greater than 0 and the exponent on the number e is called the growth constant or growth rate. And if you know the growth constant or growth rate, if you divide the natural log of 2, the number 2, which is like equal to 0.69 something, divided by k, the growth rate, you get the time for a substance or population to double in size. Solving this equation for k, if you know how long it takes for a population of substance to double in size, then you can find the growth rate k by dividing the natural log of 2 by t, the time it takes for it to double. So this is our basic model, okay, for exponential growth. So let's apply it to a couple examples. So we're given initially 300 bacteria in a culture are present. After 9 years, it is observed that the number of bacteria has doubled. So for this problem, okay, the initial number of bacteria, A sub 0, is equal to 300. The number of bacteria at t equals 9 is 600. And the time it takes for the number of bacteria to double from 300 to 600 is 9 years. So with that information, we can calculate the growth rate for this model. K is equal to the natural log of 2 divided by t, and t in this case is equal to 9. So this is the growth rate. And since we don't use calculators on exams and such, we give exact numbers. Okay. So plugging into our model, okay, we have A of t is equal to A sub 0 is 300, and k is the natural log of 2 divided by 9, and then we multiply that by t. So the amount, the number of bacteria at time t is equal to 300 times e raised to the natural log of 2 over 9 times t power. That's our model. Okay. All I did was substitute for A sub 0 and k after I computed k, because we're given the time it takes for the population to double. In B, it says how long will it take for the bacteria culture to grow to 1,000 bacteria? So we gotta find the value of t. That makes A of t equal to 1,000. For what value of t, right, is A of t equal to 1,000? You find that value of t, you want to know how long it takes for the bacteria to grow to 1,000. Well, we replace A of t on the left here with 1,000. We have 1,000 is equal to 300 times e raised to the natural log of 2 over 9 times t power. Now we're going to solve for little t. And that'll tell us how long it takes for the bacteria to go from 300 to 1,000. Well, this is a product on the right-hand side, 300 times Z, the natural log of 2/9 times E power. So we divide both sides by 300. We have 1,000 over 300 is equal to 300 times Z raised to the natural log of 2/9 times T power, divided, all of that divided by 300. On the left-hand side, right, 1,000 divided by 300 simplifies to 10/3, and the 300s cancel on the right-hand side. And so we have 10/3 is equal to E raised to the natural log of 2/9 times T power. By now you should realize the inverse function of the natural exponential function is the natural log function. So we take the natural log of both sides. We have the natural log of 10/3 is equal to the natural log of E raised to the natural log of 2/9 times T power. So we have the natural log of 10/3, natural log and the natural exponential function cancel, and we're left with the exponent on the number E, the natural log of 2/9 times T. Well, solve for T on the right, multiply both sides by 9, divide both sides by the natural log of 2, right? And we have T is equal to 9 times the natural log of 10/3 over the natural log of 2. And this is in years. Are you with me? Any questions on the math? Okay. All right, flip over your document. The bacterial population grows exponentially. The initial population is 200 bacteria. After 7 hours, the population has increased to 300 bacteria. Find an exponential model for the amount of bacteria after T hours. So the initial number of bacteria, A sub 0, is equal to 200. And the number of bacteria at T equals 7 is equal to 300. That's what we're given. Okay. So A of T, remember a model is A of T is equal to A sub 0 times E to the KT power. So A of T is equal to 200 times E to the KT power, right? I just replace A sub 0 with 200. Now we're told that A of 7, well, A of 7, put in T, 7 in for T, and A of 7 is equal to 200 times E to the K times 7 power. But A of 7 is equal to 300. So A of 300 is equal to 200 times E to now I'm gonna switch the order of multiplication and write 7k power. And now we're gonna solve for the growth rate k. Divide both sides by 200. We have 300 over 200 is equal to 200 times e to the 7k over 200. Well, on the left, 300 over 200 is 3/2. And on the right, the 200s cancel. And so I have 3/2 is equal to e to the 7k. Solving for k, so the inverse function of the natural exponential function is the natural log function. So we have the natural log, 3/2 on the left, is equal to the natural log of e to the 7k on the right. Natural exponential function, inverse functions of each other, they cancel. And the right hand side is equal to the exponent, 7k. And now I divide both sides by 7 and switch the two sides, and I get the growth rate is equal to the natural log of 3/2 divided by 7. So I put that in to my model here, and I have A of t is equal to 200 times e raised to the natural log of 3/2 divided by 7 times t power. You gotta be careful that this is an exponent and not multiplying the number e. It's not a product, it's an exponent. So in B it says how many hours will it take for the population to double? Well, the time for it to double is equal to the natural log of 2 divided by k. And k is the natural log of 3/2 divided by 7. Division by fractions, keep, switch, flip, right? So we keep the natural log of 2, we switch division to multiplication, and then when we flip this bottom fraction, we end up with 7 times the natural log of 2 over the natural log of 3/2. And this is in unit hours. Okay, we'll save the natural decay model for next.